Hello, class. My name is Scientist Zachary Bitar, and here we have Scientist Mateo Bertol. Today, it's a different topic. We're going to be learning about valence shell electron pair repulsion, known as VSEPR theory. Today, we're going to make you easily understand this topic and all the portions in it for you to easily do your work and classwork and understand it with a snap of a finger.
Just like that. Yeah.
So now we're gonna have scientist Mateo Bertol break it down of what VSEPR theory really is.
Now, the definition of VSEPR theory, valence shell electron pair repulsion theory. It basically lets us predict the shape of molecules by looking at how electrons repel each other. As we know, electrons are negatively charged, and since positive charge attracts, it will lead to similar charges repel, meaning that electrons really don't want to see each other, right? They're repelling each other as far as possible from each other. This affects how the atom arranges itself in a molecule. VSEPR theory helps us in predicting three-dimensional shapes of molecules. By this, we get to know their physical and chemical properties. Here's Bita with the explanation.
So like he broke that down, we're going to be talking about the different vocab words, like electron domains. Electron domains is a part or region around a central atom in a molecule where electrons are most likely to be found, both bonding pairs and lone pairs. Electrons' purpose is to help determine the molecular shape because electrons repel each other and put themselves as far as possible as they can. They don't want to be close. They want to be far away.
Yeah. Now you have bonding pairs. Bonding pairs are a pair of electrons that are shared between an atom. Bonding pairs can form chemical bonds, either a single, double, or even a triple bond. Bonding pairs help hold an atom together to form a structure of a molecule. This can lead to like stronger bonds and different molecular geometries, as shown in the examples below. You have the hydrogen atom with the bonding pair, and then you have these lone pairs, which Zach is going to get to in the next slide.
Like Mateo said, scientist Zachary Bita is going to break out lone pairs. Unlike bond pairs, lone pairs are a specific pair of electrons that exist independently. Remember that word, independently, from bonding with another atom. Additionally, bond angles and molecular shape get affected when lone pairs move bonding pairs towards each other. As we can see here from the examples, like Mateo is pointing at, the two electrons above and under oxygen are lone pairs because they do not connect hydrogen from oxygen because they are independent and they do not connect two atoms
together. Now we're going to talk about bond angles. Bond angles are critical in determining the shape and structure of molecules. Bonds coming from the same central atom form the basis for defining bond angles. Molecules achieve their exact shape through the evaluation of bond angles. Bond angle, like I showed, is right here, the 120 degrees, 90 degrees, 117, 112, 19, so on.
Like he talked about that, we're going to be talking about specifically the molecular shapes. So the molecular shape is the three-dimensional structure or arrangement of atoms in a molecular. The shape of a molecular affects its physical and chemical properties, including boiling point, melting point, and other different things. Exactly. So down here, we have the different shapes we're going to be talking about. Many of these shapes are hard to pronounce, so you really think that it's very confusing. But with scientist Zachary Bita and scientist Mateo Bertol, we're going to easily explain this with a snap of a finger.
Exactly. Now, like scientist Zachary said, these words do get complex, so apologies for butchering the sounds and the words. But first we have linear. Molecules that are straight and have a bond angle of 180 degrees. That's pretty simple, as I show below. Trigonal planar, a central atom attached to three atoms arranged in a triangular shape around the central atom. That creates a 120 degrees. Then you have the trigonal bipyramidal. There is a central atom bonded to 5 surrounding atoms and no lone electron pairs.
So now we have 3 other molecular geometries, like the tetrahedral, an object that has a central atom, like the one in pink, the central atom, is surrounded by 4 other atoms, the gray. So it's just one central atom in the middle connecting 4 different atoms together. Now we have the bent. A bent molecular geometry is a kind of molecular geometry in which the central atom has 2 lone pairs of electrons and is associated with 2 bond pairs. Just like we see here, the central is the pink connecting the 2 different lone pairs. Now the last one is the octahedral molecular geometry, where a central atom is surrounded by 6 other atoms. But we see here that each one that is connected to either shows 180 degrees or 90 degrees throughout the shape.
Exactly. Now, here are some examples, some, natural occurring elements. First, you have carbon dioxide, or CO2, which this is a linear one. Carbon dioxide has a central carbon with 2 double bonds, resulting in a linear shape with a bond angle of 180 degrees. Don't forget, a bond angle is the angle in which we can determine the shape of the molecule. Next, we have water, H2O. It's bent. Water has 2 bonding pairs and 2 lone pairs on oxygen, leading to a bent shape with bond angles of about 104.5 degrees. Lastly, we have phosphorus pentachloride, PCI5, trigonal bipyramidal. Phosphorus has 5 bonding pairs around the phosphorus, creating a trigonal bipyramidal shape with bonds angles of 90 and 120, as Zach specifically explained earlier.
So the 3 other examples that we provided is methane, CH4. That shows a shape of tetrahedral. Methane has 4 bonding pairs around carbon, resulting in a, like I said, the tetrahedral shape with bond angles of 109.5, as we see from the example that we provided. Now, another thing is boron trifluoride, BF3, is known to look like a trigonal planar shape. Boron trifluoride has 3 bonding pairs and no lone pairs, leading to, like I said, a planar structure with 120 degrees bond angles. Now our last element is sulfur hexafluoride, known as SF6, and it is a octahedral shape because of how it has 6 bonding pairs, and some of the bonding pairs form a 90-degree bond angle. And like I said previously, some also show a 180 angle as the straight line, as there are 2 straight lines, or you can even say 3 straight lines provided.
Right. Here's our works cited. Yeah. And thank you for watching. We appreciate your time. Science is exactly I think to say.
And we hope that with this video, you are able to understand this topic easily, like we said previously with a snap. If you did not, comment below and give us any suggestions that we can do proving to help you guys learn further on.
Right.
And any type of different topics you guys don't understand, let us know. We'll easily break it down for you in our next video. Exactly. Thank you so much.
Bye.